Good morning. Yesterday I started talking about information and entropy. Entropy in terms of this quantity where I have another on the board, Z. Z being the number of microstates, okay? And I defined a quantity W, which is not entropy in terms of Boltzmann's formula. It's defined roughly, but casually. It could be S over K in terms of macroscopic thermodynamics. Now the Z in terms of macroscopic thermodynamics I defined yesterday to be all the configurations of a system which could be, let's say, fixed mass of gas. In terms of a fixed mass of gas, it would be all the positions and velocities of the particles in there in that box. Only in the box and not outside the box. That would be the Z. But we started working with specific cases and I changed base depending on what was suitable for the problem. Now, the base 10 was suitable for the problem yesterday because I took an object with 10 slots and then 10 by 10, a 10 by 10 grid. So the base 10 worked very well because we can always apply this formula to convert and change the units. The units of information are entropy. Well, the units of entropy, there's an information part, the information part, and there's this K. K is Boltzmann's constant, which is R over NA. I did that yesterday. And it takes a dimensionless quantity, the information part, and converts it to joules per Kelvin. Physical units, same units as entropy. Now, you should check back on one of my other lectures on thermodynamics where I talk about entropy and the Carnot cycle. That's looking at entropy thermodynamically, okay? The quantity, delta Q over T. The delta Q over T. Delta Q, in terms of thermodynamics, is not integrable as it is. But put it over T and it becomes so. Okay. So today I'm just going to do some more examples. But I'll just remind you that you can get from one set of units to another. Boltzmann's law is often written in terms of Naperian logarithms, ln, log to the base e. ln, log to the base, log 10 to the base e. Where is it? Log to the base e is often written as ln. It means not natural logs. I know a lot of people say that, but originally the name was Naperian logs because this e is called Napier's constant, right? So let's continue. Boltzmann's law. Now, from the base 10, we can convert to natural Naperian logs, units, by using this factor. Okay, log x to the base e is log x to the base 10 times log 10 to the base e. It's easy to remember. It's like the same two guys, but with the 10 upstairs or downstairs. And of course, 10 can be any number. It could be a 4, 2, binary. So, we go log x to the base 10. What's log 10 to the base e? It's 2.302 many other places, so we put in for that number. So that's basically our conversion factor from log 10 to the base x to natural log. So if I use one set of logs, I can always convert to another, and vice versa. That's all I need for that. So I will keep this number. We'll do some more examples, but we'll choose a different base. I use this subscript W with the subscript 10 means units of information or entropy will be in the base 10. Binary units, bits, the base 2. E, natural units, Naperian units, call them what you want. Okay? So, S is K log W. And W, not quite, S is K times W, which is K log Z. So we're going to look at different W's, log Z's. Now we had Shannon's entropy. Now the log of pi, well, probability is going to be 1 over something. So the negative sign brings this guy upstairs and ensures a positive quantity, all right? And the PI will be various probabilities. Yesterday we looked at what happens if you throw a dice 6 times, how much information do you get? You get a single whole unit, 1 bit. Okay, or is it 6 bits? I can't remember, from yesterday. Anyway, let's look at this formula. I just project. I'm going to project it down the road. I'll be able to make this go continuous and maybe put in a P of x and a log P of x such that it could be a quantum mechanical situation. I'm thinking about that. I haven't quite figured out how to do it yet. This could be a particle in a box. What are the different states? So let's continue with our other examples for these cases here. This time I'll do a 16 by 16 grid with one particle. And there are all these little squares in here. The particle can reside in any one of these 16 by 16 squares. Now 16 by 16 cubed, that's so many units. It's a power of 2, because that's 2 to the power of 4. And you go 2, 4, 8, 16, 32, 64, 128, 256. Another power would be 512, and so on. So that's the number of squares in the box. So, for one particle, Z has a chance of being in any one of the 256 boxes or 256 states. Now I'm going to choose what kind of base I'm going to use. It looks like the base 2, or binary units, is good for this problem. So log to the base 2 of 2 to the power of 8 is 8. So in binary units, our entropy is 8 for this particular case for one particle. Now we go for two particles. The first particle can be in any of 256 boxes. The second particle can be in any of 256 boxes, because we're going to make this boson, a boson. So by the fundamental principle of counting, if there's 256 places for the first particle to stay, then for the second particle, there's 256 boxes also. If it was a boson, there would be one place less. All right? Sorry, a fermion. But we're doing the bosons. So, 256 times 256 is 2 to the power of 8 times 2 to the power of 8, or 2 to the power of 16, or 2 to the power of 2 times 8. So the W, sorry, W is 2 to the power of 2 times 8. So therefore then, sorry, that's the W. 2 to the power of 2 times 8. So we get log to the base 2 to the power of 16, or 2 times 8. That's for our 2 particles. Here's where our 2 crops in. Let's put n particles in the box. So now we'll let you digest that first. So we get, for n particles, just replace the 2 with an n. And n times 8 is the answer. All right? Is that correct? Yes. All right. Now, we also could have, I was going to go to another situation where this 8 would become a 16. I was going to make a cube of squares. But I figured you'd start getting confused. I'm going to change the issue and look at a slightly different problem. I could also work here, by the way, in the base 16, right? You'd just be changing the numbers, and I could use the conversion factor from base 16 to 2. It's quite easy. It's actually 4, I think. All right, so far so good. Now, what is the entropy? Well, the entropy, if it was a thermodynamic system, would be Boltzmann's constant times this number. Suppose n was Avogadro's number. What would be the entropy? Now we're working in binary units. So we would get AK is log, this is the entropy. We would get K times Avogadro's number. Okay, I'm just going to leave the NA in here because you're going to see what happens. Now, K is defined by R over NA. So if I let Avogadro's number be the number of particles in the box, we just get 8R. I think it's 3-1 or 1-3, I forget. Never mind. Whatever that number was, I can't remember. So let's do a slightly different example now. This one will be from relativity, black hole theory, and we'll find the W for a black hole. Now, I'm going to give you an extra piece of information here which you might find interesting. log z. Oh no, I'll keep it in the same units. I'll keep it in any units because I haven't really decided what kind of units I'm going to do yet. And the entropy of a black hole is given by 1/4 K times the surface area of a black hole over LP squared. I'm going to get rid of this for now. Now the Schwarzschild radius of any black hole is given by 2gm over c squared. Now if you put in g, and the mass of the sun, I can't remember, I think it's 2 by 10 to the power of 30 kilograms, you can look it up. Put in all those numbers and you get, for the sun, that the Schwarzschild radius is about 3,000 meters. Now, the surface area, this is Boltzmann's constant. Which is 1.38 by 10 to the power of minus 23 joules per Kelvin, which is R over NA, as I said a minute ago. That's what the K is. Now we get a factor of 1/4. And the surface area of a sphere is 4 pi R squared. In the case of a black hole, it's the Schwarzschild radius. Now this LP squared is a little unit. It's the Planck length squared. Planck length squared is GH cross over C cubed. Which is 1.6 by 10 to the power of minus 35 squared. Now I squared 1.6 a minute ago. And I got 16 squared is 256. So 1.6 squared is going to be 256. But 10 times less, because 1.5 times 1.5 is approximately 2. 10 to the power of minus 35 squared is 10 to the power of minus 70. And they're units. So, let's see what happens to the 4. 4 exactly cancels. Now, why does that cancel? I know why it cancels. People are speculating as to why it cancels. It cancels because all the information on the surface of a black hole, or even the entire universe, does not need a three-dimensional surface to specify all the possible events of the system. It just needs a flat disk. It's a two-dimensional disk. The factor of 4 was put in because some people derived it. You don't have to derive it. If we assume that all the information of a black hole is stored on a disk. Here's the black hole. Here's the disk. All the information can be put on this disk. It's called the holographic theory. The holographic view of the world. Now LP squared is downstairs. And that's what it's going to be. So let's see what all of this is. We're trying to find the surface area, we're trying to find the entropy. Let's call it K over, let's call it W instead. This is just the information, not the physics part. universe said that the radius, the Schwarzschild radius of a sun is that many meters. And this is meters squared as well. And I got 2.56. As we expect, the meters cancel and I get a dimensionless quantity, which is our information part here. This has to be squared. Actually, I'll work out this. Now, 70 plus 9 is 79. So that the entropy of a black hole, if our sun became a black hole, is 10 to the power of 80 information units. Sorry, this is the information part, okay? For our sun. Now multiply that by Boltzmann's constant to get the thermodynamic entropy, all right? Now I was going to do another one. I was going to do the entropy of the universe. I just don't have time for that one. I'll do it in a separate example. So I hope you enjoyed those calculations. It's a new way of looking at things, okay? I gave you a new piece of information, and that is that the factor of 1,4 defining the entropy of a black hole is there for a very good reason. And people haven't recognized that yet. It's dead simple. You don't need to derive it. It's there because really the information is only on a disk. And it's the surface area of that disk whereby the radius of the disk is the Schwarzschild radius. Okay? Very interesting. Thank you.